Greetings and welcome. In today's video, we're continuing our look at combinatorics and specifically looking at permutations with repetitions, which is a special case of permutation, and then circular permutations. So our first example, I have the question that says, how many ways can the letters in the word C be arranged? And notice I get 6 possible outcomes, right? Because you might think that, okay, it's a permutation of 3 choose 3, which is just defined as 3 factorial, which would be 6. And that's what I get here. However, if I don't distinctly mark to indicate the separation of these two E's, we'd never be able to tell the difference between SE1E2 and SE2E1, or these two, or these two. So the repetition is something that I need to eliminate. All right, because I don't actually have 6 possible ways that these can be arranged, since the E's are the same, right? It's a repeated characteristic here of this event. So we have to figure out how many repetitions do I have, and I guess I could ask a sub-question this way. How many ways can E1 and E2 be arranged? Right? If I can answer this question, then I can reduce my original set of answers by whatever this number is. So how many ways can that happen? Well, that would be a permutation of 2, 2, or 2 factorial, which is just 2. So what I have here is twice as many answers as I actually need, right? And I think visually speaking, you would agree that I'd eliminate this one, and this one, and get half as many answers. So my actual answer to the original problem, right? So this is wrong. This doesn't actually answer it unless the E's were distinct from one another. The way I would do it is I would do 3 factorial over 2 factorial, right? Which is 6 divided by 2, and I get 3 unique answers. So I have to divide by the number of ways I can arrange the repeated element in the problem. So the actual formula for this, since I just we somewhat discovered it, so if I have permutations with repetition, so the number of permutations of n objects I get a little bit of a crying baby there, but Mama's taking care of him. Of n objects, all right, of which P are alike and Q are alike, is the following, and this is our formula. So I'll have n objects being arranged is going to be n factorial, right? N taken n at a time. And then I'll just divide by the number of repetitions of each element. So I would divide by P factorial, and I would divide by Q factorial. And actually, if I had a third element that was also repeated, then I could also divide by R factorial, or whichever many number of elements I have. And P and Q don't necessarily have to have this be the same number, right? Maybe P occurs 5 times in the problem and Q occurs 3 times, so this would be a 5 factorial and a 3 factorial. So this is how I deal with repetitions within a problem, so I can kind of reduce my possible answers to just the ones that I actually care about. All right, so as an example, how many ways can the letters in the word parabola be arranged? So I have 1, 2, 3, 4, 5, 6, 7, 8 letters. So I'll switch colors here. So I'll have 8 factorial is the total arrangement if I had distinct letters for all of them, right? And then I've got to divide by my repetition cases. So there's only a single P. It looks like there's 1, 2, 3 A's. So I'm going to divide by 3 factorial. And then it looks like R, there's only one R, there's only one B, there's only one O, there's only one L. So in this case, I didn't have multiple repetitions like this original problem gave us the possibility for. But we can still simplify this nonetheless. So this would just be 8 times 7 times 6 times 5 times 4 times 3 factorial, right? All over 3 factorial equals, and I could cancel out the 3 factorials, and my resulting answer, looks like I wasn't prepared. Let me just grab a calculator. Is going to be 8 times 7 times 6 times 5 times 4, and I get 6,720, which if I didn't reduce it by the repetitions, the original answer of 8 factorial would have been 40,320, a number which is 6 times greater than the answer that I actually wanted. So I do in fact want to eliminate those. And actually, I might take an opportunity real quick. Let's see if I can switch over to my camera. Just to show you, there is actually a way you can calculate factorials on a calculator. So for instance, to calculate 8 factorial, what I did, I hit 8. I went to the math menu, and here's the probability menu over here, and here's NPR for permutation, NCR for combination, and then the factorial icon, so right there. So if I say wanted 8 permutation 3, I would do 8 math, go over to probability, permutation 3. So you actually have to type in the N value first, and then the R value after you kind of have called the permutation function. And it'll give you the 8 choose 3, in which order matters, right? Which is different than if I have 8 math and do combo 3. And there are far fewer results when the order doesn't matter, right? So yeah, I just want to point out that you can, using technology, calculate these. But I do think it's interesting being able to cancel some of this out on your own. So that's the first special case. Now let's consider circular permutations. All right. So example. How many ways can 4 children sit at a round table? Question mark. Now, in this case, so I've got a round table, and so I'll have an arrangement of kids, so kid 1, 2, 3, and 4. Right, and then I could swap the 4 and the 2. I could swap the 1 and the 3. I could, swap just 2 of them or diagonals and find all sorts of combinations. But it's not just the arrangement of 4 factorial, right? It's not the arrangement of just 4 kids in a line, for instance, right? That would have been 4 factorial, or 4 times 3 times 2 times 1. Which I believe is 24, if I'm not mistaken. Yeah, 6 times 4, 24. That is not going to be our answer because, in our case, some of these would be repeated. For instance, what if I put the 4 here, the 1 here, the 2 here, and the 3 here? Now, in a linear representation, right, I'm starting with a different number, right? 4, 1, 2, 3 is different than 3, 4, 1, 2. However, in terms of this circular representation, these are the same arrangements, right? 2 is still sitting next to 3 and 1, right? 2 is still sitting next to 3 and 1. All I've done is kind of rotate the object, and I think you'd agree that this is the same, and this is the same as well. So I end up having too many repeated cases because of the circular nature of the problem. So what I would do is divide by however many kids, right, I have, because there's 4 extra arrangements here by spinning, and that's what I'm going to do here. So what I would do is do 4 factorial divided by 4, all right, which is 24 divided by 4. Or there are 6 ways I can actually arrange 4 kids at a round table. Another way I could think about this, 4 factorial divided by 4, right? That's 4 times 3 times 2 times 1 over 4. And you can see that these cancel out, and it is in fact the same as just 3 times 2 times 1, or 3 factorial, which is 6. So that turns out to be the case for circular permutations. So let's define that for us, shall we? So circular permutations our formula can be defined as such: if n objects are arranged in a circle, then there's 2 ways to represent this. One would be this first way here, where I said n factorial over n, or I could represent it as n minus 1 in parentheses factorial, right? So when this was 4 factorial, 1 less than 4 was 3, and 3 factorial was my answer. So if I had 8 kids at a round table, my answer would be 8 factorial over 8, or just 7 factorial, right? 1 less than that. So those are, then there are those many permutations of the n objects around the circle. And now there's actually, even within these types of problems, there's kind of 2 cases, I guess. So let's consider this first one. How many ways can, let's say, 5 keys be arranged on a key ring? And now, in this situation, you would think that you could just do the 5 factorial over 5, or the 4 factorial situation, right? And either of these are going to equal 24, but that'll actually equal twice as many solutions as I need. And the issue is this, that, let's see if I can represent this well enough. 1, 2, 3, 4, 5. So if those are my hypothetical keys on a ring, and 1, 2, 3, 4, 5. If you imagine me having flipped the key ring over, right? That's a sad-looking arrow, but that'll do. As far as the key ring's concerned, in the arrangement of keys, it's exactly the same number and arrangement, even though they originally look different. So because of this flipping mechanism or possibility, I have twice as many solutions as I needed. So basically the situation is this. Because the object can be flipped, we divide by 2. So this is kind of a special case, so what I would do is take the 24 and divide by 2 and get 12, because it's really the same arrangement as far as we're concerned. And this could work with charms on a bracelet or different things like that. This situation doesn't apply to the kids around the table, because it wouldn't make sense to kind of flip the table or make the kids sit on their heads or something like that, right? It doesn't apply to that situation. And then there's one more type of situation that appears circular at first glance. Let's see, how many ways can 6 kids sit at a round table? If, say, one seat, I don't know, is special, or I don't know, the king's chair. Apparently these kids are pretending to be like King Arthur and whatnot. Who knows? I don't know. So in this situation, so I've got my table, and then I've got like my little king's chair here, right? And I'm having these 6 kids sit around it. So 1, 2, 3, 4, 5, 6, and then I could kind of find all sorts of different arrangements. However, because there's this one unique spot, it's no longer a circular permutation, right? I actually could think of this as a linear representation of 1, 2, 3, 4, 5, 6. The other classic type of problem like this is they'll say like, how many ways can you arrange 6 charms on a bracelet if the bracelet has a clasp? And it's the same sort of thing, like if you imagine like me unclasping the bracelet and then laying it out, it kind of changes the way the items are there, because they're now in reference to the clasp, where in this case it's in reference to this king's chair or whatever the case may be. So this is actually not a circular situation. It's linear. And because it's linear, I can represent it like a regular permutation, where it's just P 6 choose 6, which is just going to be 6 factorial, right? And let's see, what is 6 factorial? 120, is it what, 720? I don't remember. 720, yeah. Right, so so this is, I guess, kind of a deceptive problem where it at first glance appears to be circular, but in fact is not. Alright, so those are some examples of special cases of permutations. So hopefully that'll help you answer those kinds of problems, and they won't trick you in any capacity. So thanks for watching, and I'll catch you guys next time.